everyone, my name is John Emmanuel More. So today we will visualize the pre-order traversal. But before we start, you should also be comfortable with these two following concepts, the recursion and the call stack. So this is the example of our binary tree. So let's start. A pre-order traversal will always process the first node it encounters before it traverses down further. So this is really useful for topological ordering. So here's the code for our pre-order traversal. Let's visualize this traversal in the following three. So first, we start the traversal by making a recursive call to the root of the tree, which is marked as 5. As a result, we push this call into our call stack. Now that we're at 5, we process its value and then make another recursive call to its left subtree, which is 3. Here, we push pre-ordered 3 into our call stack, and our pre-ordered 3, we process this value and make a recursive call to its left subtree, which is 2. So, we pre-ordered 2 into the call stack and start executing pre-order to pre-order 2. We again process this value and make a recursive call to its left subtree 1 and push pre-order 1 into the call stack. Pre-order 1 into the call stack and prefer 1. We process the value of 1 and then make a recursive call to its left subtree, which is the pre-order of none. And we push this into the call stack. Now, we enter the pre-order none, which will hit our base case return. So we remove this call from our call stack and return to our previous call, which was pre-order 1. Since it's on top of our call stack, since we previously exit out of our recursive call to the left subtree, in pre-order 1, we can now process to the next line which recursively calls in the right subtree, which is in another pre-order of none. We push this into our call stack. Now we interpret the order of 1, which will hit our base case to return, so we pop this of our call stack and go back to our previous call, which is the pre-order 1 again. Once we go back to our pre-order 1, we see that they just exit the right subtree. So what code should we execute next? So nothing. So we're done with the pre-order 1. So we pop pre-order 1 and then 1 of the call stack and start executing the 1 pre-order to add pre-order to we exit out of the recursive call. So the left subtree. So now we will traverse the right subtree, which is nothing. Still, we push into the call stack. Since pre-order 1 of none returned, we remove this from the stack and go back to pre-order 2, which also returned. So we're now back at the 3. Our pre-order 3, which reversed the right subtree and push 4 into our call stack. Since 4 has an empty left and right subtree, we know all too familiar that what happens here with the empty subtrees. So we will skip the animation and mark 4 as done. So we pop pre-order 4 and the call stack and go back to our pre-order 3. Since we finished traversing all of pre-order 3, we pop pre-order 3 onto the 5 call stack and pre-order since pre-order 5 has 7. So right subtree, we push pre-order 7 into the call stack and we process the value 7 and see that there are no subtrees left in 7, so we are done. So we have pre-order 7 of the call stack and go back to our pre-order 5. At the same time, pre-order 5 is completed, so we can exit pop and pre-order 5 of the call stack. Since our call stack is now empty, we have visited every node that we have finished traversal.
Hey everyone! Today, we're diving into the world of algorithms with a focus on pre-order traversal. Conclusion: the pre-order traversal algorithm is a crucial technique in the study of binary trees and data structures. It's a systematic approach of visiting the root node first, followed by the left and the right subtrees, provides a clear and efficient method for tree traversal. This traversal order is particularly useful in scenarios where the structures of the tree needs to be preserved or recreated, such as in the tree cloning operation when evaluating prefix expressions in expression. Pre-order traversal is a method of visiting all the nodes in a tree data structure. In the pre-order traversal, each node is processed before any of its children nodes. This algorithm also includes following concepts: recursion and a call stack. It's a programming technique where a function calls itself directly or indirectly in order to solve a problem. It is often used to solve problems that can be broken down into similar subproblems. Each recursive call works on a smaller instance of the problem, gradually reducing the problem size until a base case is reached, which stops the call stack. The call stack is a data structure used by a program to keep track of function calls. When a function is called, the details of the call, such as the parameters, local variables, and the return address, are pushed onto the call stack. When the function returns, the details are popped off the stack. In the pre-ordered traversal algorithm, visiting the root node involved processing the root node, printing its values in this example, before moving into its subtrees. The visit occurs as soon as the node is encountered in the traversal processes, ensuring the root node is handled first, followed by its children in the left to the right manner. Pre-order traversal of the left subtree means performing a pre-order traversal starting specifically from the left child of the root node of a binary tree. This involves visiting the left subtree's nodes in the same pre-order manner. Visit the root of the left subtree first, then recursively traverse its left and right subtree. Pre-order traversal of the right subtree means performing a pre-order traversal starting specifically from the right child of the root node of a binary tree. This involves visiting the right subtree's nodes in the same pre-order manner. Visiting the root of the right subtree first, then recursively traverse its left and right subtree.
Good morning, sir. I will be presenting the traversal pre-order algorithm. So our value here is 5, 6, 7, 3, and 4, and the value is 5. So this will be our new example for the giving orders, but this is the code. So the pre-order traversal route is not important for now. It's the pre-order traversal route, the left and the right. So the important here is def insert root that values. So if root is none, we'll return. So if value is root is greater than the main root, then insert to the left and insert to the right. So let's start with the insert root, also known as our main root, also known as 0. If the 5 is none or not a child, then return the value, but he is 0 now, so will be the main, also known as the main tree. So because 5 is the main root, we'll go to the insert number 6, also known as root 6, or we can call it 1. So if the main root is the insert root is 6, also known as 1. So if the 6 is greater than 5, or value is greater than root, then root left or root right. Because 6 is greater than 5, so we go and send him to the right. So our output will be 5-6 to the right. Now this is, after the explain, we'll go to the root 7, because we are already done at number 6. So if the value is greater than root value, so we go to the left, we go to the right. I already shortcut in here because it's far more easy. Actually it's go with 7 is greater than 5, then return value because it's not a child. Then because of it, we go to the 7 is greater than 6. That's why I go there. I just shortcut. So which is yes. Then we go when we then we put 5 6 down to 7. Now then, for the next root is the 3. So as you can see, it's 5, 6, and 7 to the right. Now for the 3 and 4, this is our last value. Insert 3. So if value is greater than if the value is greater than root value, then go to the left or go to the right. So if 3 is greater than 5, then false, then go to the left. As you can see, I go back to the 5. That's what I meant when I go shortcut with number 7, because it's not allowed to go to the number 6 straight. You need to talk to the main root or your ancestors, etc. So as you can see, I explain it here. Actually, I skipped the 7 is greater than 5 because it's still the same outcome. It always stays to the main tree first before you can go to the child. So that's why I start the 5 again. So this is just example. So to show it to you that I put the 7 straight to number 6 in the other output. So today but later on I will try the 4 and represent the 4 value that will go attack the number 5 or the main root. So if the value is root, so let's start with the 4. So if the value is greater than root value, then go to the left and go to the right. So in 7 is greater than 5, less than 5. I did not give example about it, so I'm gonna give example of number 4. So as you can see, if the value is less than root value, which is true, then go to the left. If false, go to the right. Is 4 less than 5, which is true. Sorry if it's false, but it's true. So it will go to the left. As you can see here, it's go to the left. And because the value is not greater than 5, then go to the left. Then let's start with number 3. So if the value is less than root value, also known as 4, you can go to the left or go to the right. Root value is 4, is less than 3, which is false, then go to the right. The output will be, or the final output will be, is 5, 3, 4, 6, and 7. Actually, there's important details about it. I'll explain it here. So before I start, the algorithm this is pre-order traversal is a fundamental algorithm of computer science and does not have a single inventor in a part of border set of three traversal techniques which have been developed over time for use computer societies and short people. It is evident because they did not know it already happened. That's why the research rejected. They don't know they don't know who made it because it's been made like straight up. So the first background is the pre-order traversal. The start of the application, top of the node, also known as root of the tree or the main tree, stinks the greatest of the top boss of the oldest ancestor first. Like I said, will be the main tree. After visiting the root, it go down to the left side or the right side, depending on the root, depending on the less than right side. Now, after you go down of left side or first side, exploring all the nodes in the branch, once the left side is fully explored, move to the right side and explore those nodes. It depends on the number. As already said, it's on them. And the faceted traits is straightforward and easy implemented. The process is simple and can be follows as a clear pattern. As like I said earlier, the 5 it will restore if the main tree is less than or less than, it will go to the left side. But if it's greater than the main tree, let's go to the right side. It's very simple. And it's useful when you need a process to root before inspecting the subtrees, like copying a tree. So like I said, it's so easy. It would go down to the left or go to the right, depending on the numbers that was the main root. So if the main root is 100 and less than of it is 99 to the bottom of 1, then it will go straight down to the left side, to right side of the left side of the main root. There's no right side for the child. So for the negative one, or negative side of this one is not always the best for sorting if you need a noodles or sorted order. Pre-order is not the best choice in order to traversal better for that because he's always start with the main route. So take the he won't change the main route because it's a pre-order traversal. So it won't touch the main route. So if you put 100 main route there and there's a 1, he won't change the 1 in the top. It will always stay as the main route. So 100 always the main route. And for the final, can use extra space or extra space on your memory. So it's pretty big because it's implemented with a recursion and costs a lot of memory. Like I said earlier, 100 is the main root and 99 to the bottom of 1 will be your sub or child main root. So it will cost a lot of memory, also known as our gig, because it will copy the 99 to 1 to 3 properties between left, right. So it will go stuck. So it will stuck there. Alternatively, in iterative approach, using a stack can help us use less extra space. Like I said, it will take the space of your computer, so it's pretty bad at using, so no one use it. There's people maybe use it, but I don't know. Maybe they will combine it. So after that will be my friend or my team will be representing their project. So that's all.
So hello guys. Our topic is the pre-order transverse algorithm. So for example, kuha na to sa in real life na pass the message game. So we are using the binary tree. As you can see, we're using the binary tree. And the game was called Pass the Message. Let's start. So the message will start to the root, which is the person A. And the person A passed the message to the person B. And the person B passed the message to the left side down, which is the person B. And wala na may laing tao nga mapasahan sa message the person B. I-transfer siya pabalik kay person B. And then the person B passed the message to the right side down, which is the person E. Again, wala naman po'y person nga mapasahan sa message, ni-transverse na po siya balik ka person B. And si person B, ni-transverse na po siya balik sa root, which is the person A. And then person A pass again the message to the right side down, which is the person C. And the person C pass the message to the left side down, which is the person F. Again, wala na po'y person nga mapasahan sa message. Dili na pwede mo transverse, muuna na ang end sa message. So the last person nga gipasahan sa message is person F. Mo-inform siya sa message nga na-receive niya in many process. And that's how pre-order transverse algorithm works in real life. Thank you.